We are excited to introduce our great paper, Mitigating Adversarial Vulnerability Through Causal Parameter Estimation by Adversarial Double Machine Learning. The presenter is Byung-Wan Lee, and it is my honor to fully collaborate on our research with Junho Kim, the co-first author. This is our research motivation. There have been various research to improve adversarial robustness against unseen perturbations. However, we observed that it is an intriguing property for conventional adversarial defense to have unbalanced class-wise adversarial vulnerability, as shown in these figures. Even with advanced networks such as vision transformers or advanced defense methods, this peculiar phenomenon is constantly happening. To address this peculiar unbalanced phenomenon, we employ a concept of double machine learning that effectively alleviates the two major biases. First one is regularization bias, getting far away from either distribution. Second is overfitting bias, bringing bias distribution. While bridging DML into adversarial vulnerability, it is expected to address the two major biases by resembling either adversarial vulnerability distribution and becoming unbiased distribution. For bridging, we first describe causal diagram and aim to causal parameter theta, representing causal effect between worst perturbation and target class prediction. In other words, our purpose is to calculate how worst perturbation affects target class prediction by computing theta. Here, the worst perturbation is generated by the natural example using projected gradient descent. By utilizing DML described in this paper, we can precisely compute the causal parameter between the perturbation and target class prediction. Interestingly, we find out the intriguing two factors comprising in theta. First one is attacked confidence. This is derived from the paper's appendix. And second one is input gradients. Based on the previous findings, ambiguous confidence around classification boundaries and high gradient magnitude boosts adversarial vulnerability. Our findings are highly aligned with their two factors. Therefore, we aim to minimize the theta to reduce the adversarial vulnerability. However, directly minimizing it leads to tremendous computation burden due to its second derivative procedure. Instead, we approximate the procedure of minimizing theta by utilizing numerical partial derivative calculation. Then we can get lost with conventional adversarial defense, but the one difference point is the balancing ratio term, enabling us to focus on vulnerable samples by reweighting the loss. More details and their algorithm are described in our paper, so you can see our paper or our core code for concrete implementation. By minimizing the theta, we can get a high improved the adversarial robustness across all of the unseen perturbations. In this paper, we experimented wide ResNet or a DEIT structure on Cypher 100 and Tiny ImageNet either. To identify the effectiveness of ADML, we evaluated class-wise adversarial vulnerability and show ADML can alleviate this phenomenon. Now we explain what is the main point bridging DML and adversarial vulnerability. In the previous, we introduced DML's advantages, addressing two major biases. In the perspective of adversarial vulnerability, ADML can resemble either adversarial distribution and become unbiased adversarial distribution. Follow the direction of up arrow. Thank you for listening our research work. I hope you get a significant insight how we can utilize DML and what is major bias in deep learning.